Hello. So in this video, we're going to talk about what we're calling the convergence theorem. And kind of what the convergence theorem does is it tells us when a Fourier series converges to kind of the function that it's a Fourier series for. Right. And so kind of the outline for this is we're going to review, right, kind of what these Fourier series look like, what the Fourier coefficients are and how we compute them. We're going to then state what we're calling the convergence theorem, which tells us, right, where this Fourier series that we're constructing out of sine and cosine terms. The question is, where does that series converge pointwise to the given function? Okay, and so the claim will be, well, generally it converges almost everywhere you get, the convergence you'd like, but there are a few points where convergence isn't guaranteed, but we can compute exactly what the value of the series will be. Okay, so we'll state this theorem. We'll talk a little about what it means in practice, and then what we'll do is we'll talk about sketching Fourier series. Okay, and so qualitatively, sketching series will tell us a lot about what we're working with, what we're looking at, etc. But if we actually want to use these series for anything like compute or solving PDEs, then we actually need to know what the coefficients are. And so we'll end with going back over how do we compute coefficients for a Fourier series. Okay. Cool. So Fourier coefficients and Fourier series, right? So recall, right, the objects that we're working with now are series of this form, where you have kind of this infinite linear combination of cosine pieces, again, because the constant term corresponds to cosine of 0. So we have an infinite sum of cosine terms plus an infinite sum of sine terms. And so then the question is, if we're given some function f defined on an interval negative L to L, when do we have equality between this function and this Fourier series for some a sub 0, a sub n, and b sub n that we can compute? Okay, so that's our main question, right? When do we actually have equality between the left and right hand side? And so as we've seen, right, the question is, well, sure, if you want a series like this, you need to know what these coefficients are, okay? And we have formulas to compute those coefficients, right? And so in particular, right, the constant term, that's going to be 1 over the length of the interval, right, negative L to L, that has length 2L. So 1 over the length of the interval times the integral of the function, that's going to be the constant piece. And then the other pieces are going to be 1 over half the length of the interval times the integral of the function times cosine or sine. Okay, so we have explicit formulas to compute these coefficients. And so one thing to keep in mind is that, right, if we want such a series like this to actually exist, right, well, we should be able to compute what these coefficients are. And so if we look over here, right, so for example, the constant term, this is the integral of the function over the entire interval, right? And so if we want this to be a well-defined, constant that shows up in our Fourier series, then this integral better be finite, okay? As soon as this integral diverges or is infinity, then we don't have that Fourier series. Okay. Right, so the functions that generally we'll be working with are going to be piecewise smooth. And so then in particular, these integrals are always going to be well-defined. But these integrals can be defined for functions that aren't necessarily piecewise smooth, right? So if your function, tends to infinity at a point, right, for some value of x between negative L and L, it's possible that all of these integrals converge, okay? And so in that case, sure, you can compute the coefficients, you have relatively well-defined Fourier series. Yeah, so the point is the functions that we care about, all of these integrals will converge, but there are other functions where all of these integrals will converge, and so you have a Fourier series that are kind of beyond the scope of what we'll focus on in this course. Okay, so great. So we have formulas for computing these coefficients, right? And so one observation is, well, if you take this kind of this trigonometric series, and instead of summing all the way up to infinity, you just truncate the series and take the first n terms in the summation, right? Well, constants are continuous functions, right? So constants are continuous, cosine is continuous, sine is continuous. And so we're taking a finite sum of continuous functions. And so then the resulting thing will be continuous, right? So this finite series, or this finite sum, is a continuous function. Okay, but, right, the series that we care about, we don't want to just sum up finitely many terms, we want to sum up infinitely many terms, right? And so one question is, well, if you sum up infinitely many continuous functions, is the resulting function continuous? Okay. A little more broadly, if your function is just piecewise smooth, right? So it may have jump discontinuities, right? What's going to happen to this piece? Is it going to equal your function that has jump discontinuities? Okay, so this is a question that we're really asking, right? We can define the series on its own. This function f we're given, and of course, right, these coefficients are given in terms of f. But the question is, when is this infinite series exactly equal to the given function f? Okay. And so the answer is, well, in general, they won't be equal. The series, right, this Fourier series, when you add up infinitely many terms, may not be equal to the given function at every value of x. Okay, which, you know, may be a little annoying, but it's not actually going to give us any issues. Okay, generally what we're going to do is we're going to work with each of these terms, each of these pieces, kind of interchangeably. Okay, and so to be precise about it, right, technically there are cases where this series is not equal to this function, okay, but they're still related, they still behave pretty much the same. And so the notation we'll use is this tilde, right? So f of x tilde, this series here, means that this series, the coefficients are computed using this given function f. And so the two sides may not be equal, but we're constructing the series from the given function f. Okay, so they're related. Okay. Okay, right, but so yeah, so the observation here is series may not be equal to the function f. Okay, so then the question is, how close is it? When are they equal? What can we say about whether or not there's an equality here, or when we have an equality, etc. Okay. And so that leads into what we're going to call the convergence theorem, which states when the function, or when the Fourier series converges to the function. And if it doesn't converge to the function, what happens instead? Okay, so the theorem is the following. Suppose we have a piecewise smooth function, f of x. Okay, it's defined on the interval -L to L. And then we compute the Fourier series, right? So we consider a sub 0 plus the sum of a sub n cosine of whatever, plus the sum of b sub n sine of whatever. Okay, and so then the claim is that the Fourier series converges to what we're calling the periodic extension of the function, which we'll draw here in a second and kind of define by example. Okay, so it converges to this thing called the periodic extension wherever this extension is continuous. And so in particular, wherever f is continuous on the original domain, right, from negative L to L, the Fourier series will converge to f of x. Okay. And so then the question is, well, what about places where the periodic extension is not continuous? And so in particular, where f of x, the original function kind of on the original domain, isn't continuous. The theorem says that the Fourier series will converge to the average of the left and right limits, which we'll write as this, right? So this is going to be, say, the right limit, right? You're approaching x from above. This is going to be the left limit. You're approaching x from below. And then you're taking the average of those two values. Okay. Cool. So this is a theorem, right? Generally, wherever your function is continuous, the Fourier series will converge to that function. Wherever the function is not continuous, the Fourier series will converge to the average of the left and right limits. Okay, so let's see what that looks like. So here's a function, f of x equals x in the interval negative L to L. Okay, so what we're going to do is we're going to draw our axes. Let me draw this a little further out. And then I'm just going to extend this way. Okay. And so then our function from negative L to L is just going to be the function f of x, or sorry, f of x is equal to x on this interval. Cool. Great. So if we go back to the convergence theorem, first statement is, right, well, where does the Fourier series of x converge? Converges to the periodic extension of our function, wherever the periodic extension is continuous. So what we're going to do is we're going to sketch this thing called the periodic extension. Okay. And so here, right, so really what are we looking for in the periodic extension? We want the function, right, whatever function it should be, such that if you ask what the value is, okay, if you take an x value kind of one period further along, this should be equal to the x value kind of, right, without adding that period. Okay, and so in particular, right, so here, so let's draw the periodic extension in green. So plug in x equals 0. We want the value of f, the periodic extension, at the point 2L to be equal to the value of f at 0. Okay, so at 2L, the function should be 0. And likewise, right, so we took this point plus 1L plus 2L. So if we take points down here, plus 1L plus 2L, periodic extension over here is going to look like that. If we take points over here, plus 1L, so plus 1L plus 2L, periodic extension over here is going to look like that. Okay. So what we've done is we've sketched the periodic extension, right, of the purple graph, the curve. We've sketched a periodic extension kind of one period to the right. But of course, you know, so here if you add plus 2L, or say plus 4L, so 2 more L, right, you're going to get x plus 4L which is x plus 2L plus 2L. So that's going to be equal to f of x plus 2L, which is equal to f of x. So the point is, right, if we're sketching the periodic extension, sketch the same thing over there, and then keeps going over there. Likewise, going the other direction, we'd expect the periodic extension to look something like that. Okay. And so note that on the interval negative L to L, right, not including the endpoints, this function is continuous. Okay. So our Fourier series converges to the function on this interval. Okay. So what we have here, these lines, these are all the sketches of a0 plus the sum of a sub n cosine pi over Lx plus the sum of b sub n sine of n pi over Lx. Okay, so what we're drawing here is exactly this infinite series, right? Because the convergence theorem tells us that, right, on this interval, on this interval, on this interval, this series converges to the periodic extension of this function. Okay, so what we're sketching here so far is exactly this series, right? We don't know what these constants are. We don't know what a0, a sub n, and b sub n are, but qualitatively we can sketch what the series looks like. Okay, right, so we've sketched the series kind of on the interior of each of these intervals. Right? So now the question is, well, what does the series look like at these points? Right, and so keep in mind at these points, we have a jump discontinuity in the periodic extension. So if we go back to the convergence theorem, right, wherever the periodic extension of f of x is not continuous, right, what does the Fourier series converge to? Well, it converges to the average of the left and right limits. Okay, okay, so this value right here, right, f of x equals x, evaluated at x equals L. This point here is L. Okay. So the question is, well, what is this point right here? Okay. We got this point by taking the periodic extension. So here, this value, so maybe we can write it like this. So this value right here, this is f of, and we can write it like this. This is f of minus, all right, okay. So the x coordinate is L. So let's write f of L. But now let's use the fact that it's a periodic extension and then factor out this 2L. So this is going to be, so f of L is equal to f of minus L plus 2L. Right, because sum these together, you get back L. And so by the fact that we're working with a periodic extension, whenever you see a 2L, right, well, for a periodic extension, f of x plus 2L is just f of x. So the value here is equal to f of minus L, which, looking at that, is going to be minus L. Okay. So the question is, right, what is the value of the Fourier series at x equals L? Well, it's going to be the average of the left and right limits of this periodic extension. The left limit is L. The right limit is negative L. So the average of those two is going to be 0. Okay. So the value of this series, right, the value that this series converges to at x equals L is exactly 0. And so likewise at any other point, so at negative L, the value of the series converges to a 0. At 3L, it's going to be 0, 5L, it's 0, etc. Okay. So what we've done here is we've sketched the entire Fourier series. We don't even know what the coefficients are, okay? But we know what the graph of this series looks like. From negative L to L, kind of on the interior, and then from L to 3L on the interior, etc. The graph of the series looks like this. And then at negative L, L, 3L, 5L, etc., the value that the series takes is 0. Okay. Cool. And so in particular, right, the series and the function, right, they don't agree necessarily at these values, right? Because f of x at x equals L, the value is L, but the Fourier series, the value is 0. Okay. Right. So the function and the series don't agree, but turns out it's not too bad. But yeah, anyways, okay. Cool. Right. So we don't know the coefficients, but we know what the Fourier series, the sketch of this thing looks like. Okay, so let's take a look at another example. So here we're given the function f of x, which is equal to minus L minus x on the interval negative L to 0. And it's equal to the function L minus x on the interval 0 to L. Okay. So let's sketch this. Let's see what it looks like. So negative L, L, 2L, 3L, etc. So what does the function look like? Let's see. So plug in negative L here. And so the question is, what's the value here? Plug in negative L. You're going to get minus L, which is plus L. So minus L plus L. It's going to be 0. Okay. This is a linear function, slope negative 1. And so then the question is, what is the value at x equals 0? We'll plug in x equals 0. Value is going to be negative L. And we're going to include that point. Okay, so that's the graph of the function on this half interval. What about the other half? Well, at x equals 0, this is going to be L minus 0, which is L, okay? But this is, x is strictly larger than 0, so we don't actually have the value of L, so we're going to draw an open circle. Otherwise, at x equals L, right, L minus L is 0. So we have a linear, we have a line segment between this point and this point. And so then something like that, and that's our function. Okay. And so, right, the question is, well, where does the Fourier series for this function converge? Okay, if we wanted to, we can compute the Fourier coefficients and we could write out explicitly what the Fourier series is. But here we don't really care about that. We just want to have a qualitative sense of, you know, what the Fourier series looks like. Okay. And so, of course, to do that, well, let's take the periodic extension and then see where that periodic extension is continuous. And that's exactly where the Fourier series converges. Wherever the periodic extension is discontinuous, the value of the Fourier series will be the average of the left and right endpoints, or left and right limits of that periodic extension. Okay, so for the periodic extension, take take the graph of the function over here, copy it over there. So that's going to look like that. And then copy that down. and it's going to keep going. And that's going to keep going. Okay. So here we have sketched the periodic extension of our function, or periodic extension of the function where it's continuous. And so then the question is, right, what's happening at the points of discontinuity or the jump discontinuities? And the value of the Fourier series at those jump discontinuities is going to be the average of the left and right limits. Okay. The left limit here, this is L. The right limit, the right limit here is L. The left limit here is minus L. And so again, their average is going to be 0. There's 0, etc. Okay, so again, we see that, right, this is a sketch of the Fourier series, okay? And in particular, at x equals 0, the value of the Fourier series is 0, whereas the value of the function is negative L. And so what's interesting to note is if we change this definition so that instead of this function being equal to minus L minus x at x equals 0, if instead we change it so that the function is equal to L minus x at x equals 0, right? Well, changing the value of the function at the single point 0, right? So instead of, if this was filled in and this was an open circle, right, that's not changing the left and right limits. And so then the value of the Fourier series is going to be unchanged. Okay. And so in some sense, right, the Fourier series doesn't care about individual function values, right? And part of that comes from, right, the fact that, well, we compute these coefficients using integrals, and integrals don't care about the value of a function at a single point. But anyways. Okay, cool, right? So these are, two initial examples, right? We don't know what the coefficients are. We just know qualitatively what's happening with, what's happening for these Fourier series. And so a technique that we used was actually sketching what these series look like, right? And where they converge. And so then the next piece here is, well, let's formalize the rules that we used a second ago, informed by, right, this convergence theorem and where we know these Fourier series should converge. Okay, so how do we sketch these Fourier series? How do we qualitatively get a sense of, what these series look like? So how do we sketch them? Well, right, as we saw, sketch the function on that initial interval. Okay. Next, sketch the periodic extension of the function, right? And so what this looks like in practice is you take that same sketch, right? Take that template and then copy it over 2L, copy it over 2L, and then you can also go the other way. So take that template, move it back, etc. So you're sketching this periodic extension of your function. And right, mathematically, what do we mean when we say a periodic extension? Well, it's the function such that if you wanted to define the function outside of the interval, you define it so that it satisfies this property. Okay. And so when we sketch the periodic extension, especially wherever that periodic extension is continuous, then, right, that's the sketch of the Fourier series. The only thing that's missing is where this periodic extension is not continuous, right, where the jump discontinuities are. And so what we do is, well, finally, we mark an x at the average of the left and right limits, right? Because that's what the theorem tells us the value should be. Okay, cool. So let's see what that looks like one more time. So here's a function, f of x, defined on the interval negative L to L. how do we define it? Well, it's going to be 0 for x less than L over 2. And it's going to be the value 1 for x greater than L over 2. Okay, and so keep in mind, this is not saying what's happening at x equal to L over 2, right? But the observation was, well, it doesn't really matter because all that matters are the left and right limits. And so if you just change the value at a single point, it doesn't affect the left and right limits, so it doesn't affect the value of the Fourier series. Okay, but let's go ahead and sketch this. So same axes, negative L, L, 2L, 3L, 4L, and then we should go out to 5L. Okay, so what does the function look like? Well, let's figure out where L over 2 is. It's right there. So for x less than L over 2, right, and again, on the original kind of domain of definition, so implicitly x is less than L over 2 means x is between minus L and L over 2. Okay, but for this interval, the function is 0. So our sketch will look like this. Okay. Now, for x greater than L over 2, and then implicitly x between L over 2 and L, the value of the function is 1. So it's going to be something like that. Okay. And the value, the value of f at L over 2 and L, and in particular at negative L, value doesn't really matter. Okay, so we've sketched, so if we go back, so we've sketched what f of x is between negative L and L. And so now we sketch the periodic extension. As I said, right, this, what does this entail? Well, take kind of the form of the function or the graph or template, whatever you want to call it, take that, copy it over to the next interval. Okay, so we're going to take this form, copy it over there. Okay. And so then for x about there, it's going to be the value of 0. And then for x between, right, so halfway between the midpoint and the endpoint. So here, 0 to L, shift by 2L, we're looking at 2L to 3L. Halfway between there, the value of the function is going to be 1. Okay. So this is sketching the periodic extension, say 1 period over. Do the same thing one more time. So it's going to be something like that. And then the value of 1 right there. Okay, so what we've done so far, sketched x, and then we've sketched the periodic extension of f of x. And so now what we need to do is we need to account for, right, these jump discontinuities. And the way we account for them is we've been marking x at the average of the left and right limits. Okay. So the question here is, right, where are the jump discontinuities? Jump discontinuity there and there, right? But kind of these two jump discontinuities repeat again and again, and then also backwards, etc. So we figured out where the jump discontinuities are. Now we need to figure out what the value is there. Okay. But as we've been saying, the value at these jump discontinuities is going to be the average of the left and right limits. So here, the left limit is 0, and the right limit is 1. So the value at that jump discontinuity of the Fourier series is going to be about 1/2, or will be 1/2. Likewise over here, the left limit is 1, the right limit is 0. So the average of those two is 1/2. Okay. And so then copy those values over. We're going to get a sketch like this. Okay. So what we've sketched right here is the Fourier series of f of x. So this is a sub n cosine of n pi over Lx plus the sum of b sub n sine of n pi over Lx. Right, so all of this stuff right here is the sketch right here. Whereas f of x, this just consists of these pieces, or sorry, f of x really just consists of these pieces. The periodic extension of f of x consists of this and this and this and this and this and this, etc. But that's cool. Okay, so we've sketched the Fourier series. Okay, and so one question is, well, what does this tell us about, right, what values this takes? So one thing we can do is actually explicitly write out, right, what these values are. And so if we look over here, right, so this jump discontinuity, by the fact that we're looking at a periodic extension, should be copied over here. So the value there is 1/2. And so what we can do is we can actually explicitly write out what values this Fourier series takes, right? So at x equals negative L, the value of the series is 1/2. But strictly between negative L and L over 2, the value of this series is 0. At x equals L over 2, the value of this series is 1/2. Strictly between L over 2 and L, the value of the series is 1. And then finally, at x equals L, the value of the series is 1/2. Okay, and so we don't even know what the coefficients are, right? But we know what the entire series, right, what values it takes. Right, and so what I just said is summarized here, right? We don't know what these coefficients are, but from the sketch of the Fourier series, we know what all of these values, right? What values the series takes at various x. Okay. Cool, right? But yeah, so takeaway for all of this is, right, if we want to qualitatively get a sense of what these Fourier series look like and, you know, what general properties of them are, we can sketch them, and we have a procedure for sketching them based on this convergence theorem. Okay. Okay. Cool. Right, but so yeah, sketching Fourier series is nice and all, okay, but if we actually want to use a Fourier series for anything, right, we actually need to compute the coefficients and use those coefficients, okay? So in this last bit, right, we'll just kind of review, right, what it means to compute these coefficients, right? So if we want to use these Fourier series for anything like, right, actually solving PDEs, we need the coefficients. How do we compute the coefficients? We have formulas for them. Okay, and so keep in mind, all of these formulas, these are defined. So these work for f of x defined on negative L, or let me write it like this, defined for negative L less than or equal to x less than or equal to L. Okay. If you have a function defined on 0 to L, these aren't quite the formulas. There's a little tweaking you have to do. Okay, but generally we'll define functions from negative L to L, and then we can use these formulas to compute the coefficients. Okay, right, but we've already had a lot of practice computing these coefficients. Okay. Right, practice, it comes out to just computing these integrals. Okay. And so the question is, right, well, for this function that we looked at before, right, question is, what are the coefficients? Okay. And so It's probably no surprise, right? Well, if we just use the formulas, we can explicitly compute what these are. So for the constant term, okay, by definition, this is what the coefficient is. Okay? And so to actually evaluate this, since our function is defined in a piecewise manner, right, we have to split up the integral. So first we evaluate the integral from negative L to L over 2, and then plug in the value of the function, right? The value there is 0. Otherwise, we integrate from L over 2 to L and plug in the value of the function. There, the value is 1, okay? And so then this constant term is going to be 1/4. Same thing with the other terms, right? So for a sub n, which are the coefficients for the cosine pieces, okay? By definition, this is what the coefficient is in terms of, right, f of x, okay? Same as up here, right? F of x is defined in a piecewise manner, so you have to break up the integral. The piece from negative L to L over 2 is 0, so we don't see that. So we're just left with the integral, or 1 over L times the integral from L over 2 to L of 1 times cosine n pi over Lx. Okay. Integrate cosine, you're going to get sine. This comes out, well, 1 over this comes out, so you're left with 1 over n pi, sine of n pi over Lx, evaluated between L and L over 2, and that's going to give you this expression. Okay. So one point we can make right now, right? Well, here we have a sine of n pi. Okay. And so if you sketch what sine looks like, right? So that's 0, pi, 2 pi, etc. 3 pi, right? So the observation is that sine of n pi is always 0. Okay. So one simplification you could do is plug in, well, this is always 0, so just substitute this with 0. And that's a perfectly fine, simplification you can make for these coefficients. Here, we're just going to leave it like this, not worry about simplifying it. But yes, if you wanted to, you could simplify this to 0. You could simplify this, right? So whenever n is even, n over 2 for an even n is going to be another integer. So then for n even, this whole thing is 0. Okay. And so what that tells us is that a sub n is going to be 0 for even n. Okay. If you wanted to make that simplification, you can. For now, we won't. Okay, so those are coefficients for the cosine pieces. We can do the same thing for the sine pieces, right? So b sub n, what are these coefficients? Well, they're 1 over L times the integral from negative L to L of f of x times sine of n pi over Lx. Right, f of x is 0 from minus L to L over 2, and it's equal to 1 from L over 2 to L. So make that simplification, your integral becomes this. Okay. Integrate sine, that's going to be minus cosine. You're going to have an n pi over L, or 1 over that, come out. So you're left with this. Plug in, you're going to get this. Okay. And so here you could make a similar sort of simplification. Cosine of n pi looks something like this. So this is 0, this is pi, this is 2 pi. Okay. So cosine of n pi is always going to be -1 or 1. Okay. So if you wanted to, you could substitute, right? So when n is even, so like here and here, it's equal to 1. So if you wanted to, you could substitute -1 to the n for cosine of n pi, and that would be totally valid. Here, we won't make that substitution. We'll just content ourselves with, yes, we can compute the coefficients in some way and actually get what these coefficients are. Okay. Cool. So the main takeaway here, right, from all of this is the convergence theorem, right, which again says, great, we have a function, it's piecewise smooth, we can compute its Fourier series. When is the function f of x equal to its Fourier series? Well, the function is equal to its Fourier series, well, rather the periodic extension of the function is equal to the Fourier series wherever the function is continuous, or its periodic extension is continuous. Otherwise, the value of the series is going to be the average of the left and right limits. Okay. What this lets us do is it lets us sketch Fourier series and get a qualitative view of what these series looks like, or what these series look like, which is great. But if we ever actually want to work with these things, like say solving PDEs, then we really don't have much choice but to actually compute the coefficients. Great. And so up next, right, so one point I made was, well, right, all of these formulas work when your function is defined from negative L to L. And so then one question is, well, what if you only know the function from 0 to L? Can you still use this framework? What do these formulas look like, et cetera? And that's what we'll start talking about in the next chapter.